So let's now get back on basis functions. So we will overview what we have seen last week on this notion, because it is important. We will build on that. So some recap on the XOR problem. So when we have an exclusive OR problem, we are looking for a case that is simplified as this one. We have 3 data instances, so 3 cases. So we see that 0, 0, and 1, 1 are both assigned to a class of 0, for example. So they correspond to the blue cross here, and the red stars here are corresponding to the 2 middle cases. So this is a simple problem. It is, I would say, a simple example of non-linearly separable data set. And as such, we can solve it by we can use what we call a basis function. So this basis function is making a nonlinear transformation from a d-dimension space in Rd to a new space in k dimensions. So that transformation is mapping things into a new space, but we still can solve it using something that is similar in terms of what we had before in terms of linear discriminant. But with this equation, you see that the big difference is the fact that the x is applied in the function phi ij here, which is making the mapping from Rd to Rk. Some examples of function, we have this one, which is basically the identity. It's doing nothing but getting back to the linear formulation, but we have some other formulation like this one, which is RBF, for example, that is allowing us to map this into a new space with k being possibly much bigger, much higher dimensionality than D. So an example of that is like this mapping from 1D to 2D. So we have an example of like 3 samples, which in 1D are not linearly separable, because for being linearly separable, we would need to be able to split this with 1 threshold. But here it is not possible. We need 2 thresholds. We need a threshold that is kind of splitting it here and there, saying that the zone in the middle is for the red class, and the rest is for the blue class. And this is impossible with 1 threshold to solve. So this is non-linearly separable in 1D. But if we are making the mapping with x map into 2D with the first dimension, which is x, and the second, which is x squared, we get into that setting. So now we have a setting in 2 dimensions. Of course, in these 2 dimensions, the only valid solutions are around according to that curve. But the nice thing with that is that if we can just have one separating upper plane, we could just cut it there. And we just say that here below, it's for the red class. So on down is for the red class, up is for the blue class. And we have it solved. We are able to solve this, and this discriminant is linear. So in 2D, it is linearly separable. So there are some basis functions available. For example, for the XOR problem, we can get into a new one. We could just map from 2D to 3Ds. So with x1, x2, which are the same thing than before, plus x1 times x2 here. And making that mapping in 3D, we have something like this. So we have this mapping in 3D, and we can see that it is linearly separable, and we could just get some kind of hyperplane there going in between the blue cross and the red stars. And we are able to split. We see just over it's for, on the top is for the blue cross, and below is for the red stars. And we have it itself. So the data is linearly separable in the new space. There are things like radial basis functions, which is a more fancy basis function that is quite used, which is making a projection that is similar to some kind of Gaussian distribution, simplified to this thing. So basically, it's the exponential of x minus mi squared with the L2 norm on that, divided by 2 times si squared. Consists of a Gaussian function centered on mi with a local influence parameterized by si. Strictly speaking, this is not a probability density for a multivariate lab, because if we integrate this function between minus infinity and plus infinity, it is not equal to 1. So it's not a PDF, but it is similar to a Gaussian distribution in terms of its formulation. So the idea is to have some kind of Gaussian functions that is put in the space that is centered on the MIs, and we have this at different places. And so for each dimension that is resulting from all of this Gaussian function, we are measuring the distance from that MI modulated according to the shape of a Gaussian function. With K Gaussian functions, the projection is done that way. So we have K Gaussian functions put in that space. K might be much bigger than D. So if we are looking in 10Ds, that we can put 50 different Gaussian functions in 10Ds, we will map from 10 to 50Ds.